Okay, so real quick, what you need today, reference table. Always need reference tables in this class. You're going to need a piece of paper. Doesn't matter if it's lined or not. If it looks like this, you're all good. Need a pen or pencil. You need some scissors. You are going to watch this first. Use the material you come up with in this on your activity, and then you're going to use it on the quiz that you're going to have today. All right. So radioactivity, what is decay? What does that have to do with what we're doing? Well, COVID-19, it has to deal with half-lives. And COVID-19, scientists figured out how long it stayed on surfaces using half-life. How much of the coronavirus decayed or became inactive over time. So as you can see, they found out that on cardboard, it lasted about 4 hours before it decayed. And after 24 hours, only 98% of the virus was inactive or should be inactive. So that's a lot. All right. So with radioactive decay, say I put an orange on my desk at school and I let you guys watch it. The whole school year, I didn't even touch it. You guys were watching and you're like, what the heck is she doing with this? Well, you would notice over time that it would start to shrink and get smaller and smaller. So when I started it, it'd be full, 100%. And then say we have its half-life. I'm not going to tell you what the half-life is yet. But after the first half-life, 50% would be left. After the second half-life, remember, I'm going to cut it in half. Half of this would leave me with 25% left. Half of 25 is 12.5%. Half of that is 6.25. And half of that would be way too small for you to see, 3.125. Well, how long would it take for an orange to get down 50%? It'd take 3 months. So the first 3 months of school, you would see that it would shrink half. Well, 3 months later after that, or at 6 months, 25% of that original one would be gone. Well, I'm going to add 3 more months on because that would be another half-life. 9 months later would be 12.5% of that would be gone. 12 months later, the next year, 6.25. So if you came back the next year and been like, oh, what's going on with that orange? Half of that 12.5, it would be even smaller. And at 15 months, it'd be 3.125% of the original 100% would be left. Fraction-wise, 100% is 1 over 1. Well, what's fraction of 50%? 1/2. What about 25%? Think of like quarter. A quarter is, there are 4 quarters to $1. So 1/4. But look at this. If I did 1 over 1, that bottom, if I times that by 2, it'd be 1/2. Now, if I times this bottom by 2, I'd get 1/4, because remember, I'm not touching that top. So if I times the bottom, leaving the top alone, I'd get 1/8. That's 12.5%. Do it again, times by 2, I'd get 1/16. Times by 2 again, I'd get 1/32. All right, so this is how you are going to think of half-lives in fraction form and in the top part. So percent form, I'm starting with 100% of that styrofoam cup. I left it out. Half-life goes by. I'm left with 50%. Another half-life, 25, 12.5, 6.25, 3.125. Well, how many years would that be? Well, it takes 1,000 years for one half-life to go by. I'm going to add 1,000 years to that for my second half-life. I'd be stuck with 2,000 years before 25% is left. Think of this, all that styrofoam you throw out from all these restaurants. I'm going to add another 1,000 to it. 3,000 years later, I'd be left with 12.5% of the original. Another 4,000 years, or not another 4,000, but in 4,000 years, I'd be left with 6.25. 5,000 years after my original creating that, 3.125% of that would be left. That's a long time. All right, so let's get into writing some notes. So we're going to look at carbon-14. Why? Because that's one of the elements that we really want to focus on. And it's in your reference table. Where? Right up here at the top, radioactive decay data. So if you're looking at that, it says, so first off, it is slightly radioactive, carbon-14. That has a half-life, and it does say the half-life right here. Am I on the wrong side? Oh, right there. So half-life is there, 5.7 times 10 to the third. So when I take that out of scientific notation, I take this decimal, move it to the right 1, 2, 3. I'm left with 5,700 years. So carbon-14 is found in plants and is replenished every time you eat vegetables or meat that from animals that have eaten plants. So you're eating all this stuff every time you eat, you ingest carbon-14. But as soon as you die, that carbon-14 starts to decay, and it turns back into nitrogen-14. How do I know? Well, that would be right here in the disintegration. You see that carbon-14 goes to nitrogen-14. And then you got potassium goes to argon or calcium, 40. And uranium goes to lead, and rubidium goes to strontium. And again, if you need help with those, they're on the back page, the letters. All right. So nitrogen-14 is very stable. It doesn't do anything after that. It doesn't break down. So at that point in time, when you die, you've had as much carbon-14 as you will ever have because you can't ingest any more. So you will no longer gain any more carbon-14. All right. So this is where that piece of paper comes into play. What I need you to do is you are going to take that piece of paper and you are going to fold it in half and you're going to cut it in half. You're going to take one of those pieces of paper and you are going to write down all of this information. So what are you going to write down? Well, at the first half-life, which is 50%, it is also your it's a half-life, first half-life, and that's 5,700 years. I would like you to take the sheet that you didn't use, fold it in half, and you're going to cut it. Then you're going to write 25%. Well, at 25%, that's going to be a quarter. 11,400 years. It's your second half-life. All right, you're going to have those. You're going to do it again with the extra piece of paper that you're left with. Cut that one in half. And you're going to put 12.5%, because look at right here, it goes over here. That's the 12.5%. It is 1/8. 100 years, third half-life. You're writing that all down. Pause if you need to. On your fourth, because you're going to cut it again, you're going to have 6.25. There's going to be a 16th. It is 22,800 years. That's your fourth half-life. Then your fifth half-life, because you're going to do it again, that's 3.125. It's 1/32. 28,500 years, fifth half-life. And then finally, you're going to go down to the 16th, or the 6th, which is this number right here. You're going to write that right there. 1/64. 34,200 years is your sixth half-life. Very important you do this. You need it for the rest of the stuff later. So carbon-14 is only useful for living things less than 50,000 years old. Well, why? Because at that point in time, the percentage of the carbon-14 left is too minute, too small to register. Well, then you've got potassium-40 that is also used on living things, which are older than 50,000 years old. So what you should do, because you can find them on here, I would color them green, just to let you know that they're living, organic. And they're older because the half-life, is 1.3 billion years old. What you got right there? All right. For rocks, which you should color the other two brown, you have uranium-238, which has the half-life of, right there, 4.15 times 10 to the ninth, or 4.5 billion years old. Or rubidium-87, which has a half-life of 49 billion years old. All right, so here's a couple questions we're going to go over real quick. What is the half-life for C14? Look in your reference table. It's right there. Look on your number 1 half-life sheet right here. It tells you right there, 57,000 years old. Why is C14 typically not used to date something older than 50,000? Well, because it would be too small to measure accurately. Okay, what if I find dinosaur bones from creatures that lived 1 million years ago? I would want to use what radioactive element? So 100 million years old, that's older than 50,000, so you would want to use potassium-40. If I want to date rocks, what radioactive elements would I want to use? Element or elements. You could use either U-238 or rubidium-87. If you want to be more precise, you want to do this one because it's more specific. What radioactive element is closest to the age of the Earth? Uranium-238. Remember, the Earth is 4.6 billion years old. This is 4.5 billion years old half-life. Which radioactive element has the longest half-life? That's that rubidium-87. How do I know this? It says it right there in my reference table. If I find a bone that has gone through 2 half-lives, how old is that sample? Now, how do I figure that out? First off, I'm going to put down 1. I'm going to put an arrow. I'll go to 50. I put another arrow that goes to 225. So those arrows signify half-life. So you're going to draw in 2 arrows, 1, 50, 25. Pretty easy. So how old is it? Well, 1 arrow is 57,000. 2 arrows is 11,400. How would I also know? That lovely piece of paper that I had you just cut up and write on? Look, 2 half-lives gives you 11,400. How much is left in that sample? Well, it says it right here, and it also says it right here, 25%. If I found 6.25% as much C14 in a living person, how old was that person when they died? Well, doing it the long way, I would go 1, 2, 3, 4. All right, so I have 4 half-lives. Well, 4 times 5,700, that gives you 22.8. Or I look at this sheet of paper that has this, and there's my answer right there. See why I told you to use it? Very good. Say I had 400 grams of C14 in an original sample. How much of it will be left after 22,800 years? So what I'm going to do is I'm going to work backwards. I'm going to start with how old, and I'm going to write down 22.8, 17.1, 11.4, 57. So I know that's 4 half-lives. All right, so if I know it's 4 half-life, 4 arrows, I'm going to start with 400, and I'm going to put 4 arrows down. Then I'd go, what's half of 400? 200. Half of that is 100. Half of that is 50. Half of that is 25. I'd be left with 25 grams. Okay? So the last but not least, if I had 300 or 200 grams of U-238, how much would be left after 9 billion years? So I'm going to look at that 9 billion, and I'm going to go back. So if I put 9 billion, half of that is 4.5 billion. I stop right there. So I write those 2 down. 9 and 4.5. That's 2 half-lives. So what do I do? I put 200 grams and then the arrow right above, right there, and it goes to 100 grams because 200 divided in half is 100. Divide that in half is 50 grams. That's how I get 50 grams. If you guys have any questions, please, please, please get a hold of me on Zoom. I'll walk through it with you. Make sure to do the activity, then the quiz. Talk to you later. Have a great day.